Swayam Prabha. Digital India. Educated India.
Welcome back. So, let us continue the discussion on the spray and the spray modeling challenges. So, what we have so far discussed on the single droplet combustion, evaporation rate, their lifetime and all this. Now, from single droplet combustion, we are now trying to look at what happens in the spray. So, this is where we have actually stopped in the last class. The spray goes through these primary atomizations, secondary atomizations and all this. Now, this will give you a complete picture how the turbulent spray combustions are actually handled. So, this is your atomization. Now, the spray comes in here where there will be two phase coupling, there would be wall impact, breakup, then there will be droplet dispersion and then evaporation takes place. So, where gaseous fuel technology, evaporation rate, and then there could be evaporation source and the mixing takes place, and then the combustion where due to turbulence chemistry interaction, and then finally it goes to turbulent spray combustion where you get this soot and all this. So, that gives you a complete picture. So, here the atomization to turbulent spray combustion, in between there will be spray, after that it evaporates, mixing, then the combustion, and finally you have a complete picture of turbulent spray combustion. Now, if you put a summary of these things, now the polydispersity of dispersed phase particles and droplet introduce a range of length and time scale, which is very important. Then the interaction of these polydispersed particles with the carrier phase turbulence, that is inherently multiscale in nature, which complicates further the modeling part. Then the particle volume fraction in conjunction with the level of particle fluctuating velocity determines the relative importance and their collision effects. And then the PDF of velocity could differ significantly from the equilibrium Maxwell distribution. Now, these nonlinearities, multiscale interaction, non-equilibrium effect, which lead to actually new phenomena such as preferential concentration and clustering that have significant impact in the multiphase flow application. So, essentially these are quite challenging. Now, it is not very uncommon to encounter a wide variation in the dispersed phase volume fraction in the same multiphase flow. For example, in a fluidized bed, the particle volume fraction can range from near closed packed at the base of the bed to less than 5% in the riser. So, these are the things one has to. Now, the approach, when you go down to the dilute spray models, how you handle that. So, there is a Eulerian approach and there is a Lagrangian approach. So, as the Eulerian approach suggests that the both disperse and the carrier gas phase are treated in Eulerian framework. So, it is a two fluid approach and represent the average size and average velocity of the droplet. This is more suited for dense flow volume fraction greater than 0.001. Development are still in progress. Now, Lagrangian approach, the droplet or particles are presented in Lagrangian reference frame and the carrier gas phase is handled or represented in a Eulerian frame. Now, the transport equation of the droplet distribution DDF or a number density function NDF spray equation is solved. Dilute volume fraction with approximation of this. Now, another advantage of the Lagrangian approach over the E, that two fluid theory is its inability to accurately represent the collision in the presence of flow. So, it is quite well known that interaction with the ambient flow can significantly alter the collision characteristics in particle laden or droplet laden flow, and the effective restitution coefficient is a function of particle droplet Stokes number. So, these effects are incorporated in Lagrangian approach Also from a numerical standpoint, it minimizes the numerical diffusion in dispersed phase. Now, if we compare that both these phases, Eulerian and Lagrangian approaches, you have a constitutive relations. Closure approximation are mostly heuristic or empirical in Eulerian approach. LE approach is computationally expensive, very difficult. So now one can think about the captures the nonlinear multiscale interaction and non-equilibrium effects in multiphase flow, accurately represent collisions in the phase of the flow, could be easily incorporated. In the Lagrangian approach also minimizes, Lagrangian Eulerian approach minimizes the numerical diffusion in dispersed phase, but it requires computationally higher cost. Now, one shortcoming in Eulerian approach is the crossing trajectory problem. Evaluation of the droplet diameter distribution is also difficult. Incorporation of range of droplet sizes, nonlinear dependence, but Lagrangian Eulerian approach can capture the nonlinear multiscale interaction. And also there are different droplets model. Now, dilute flow, point particle approximation, these are the some other things. Now, the droplet distribution function, the DDF is defined in such a way that this is how you define. Now, the velocity dependence of the DDF is not primarily important because this, so this would be du, this is also u. So, similarly integration over this will distribute the function the FD, and the simplest form of droplet size distribution can be FD, which represents the fraction of particles, and you can see the FD is dN by dt. This is accurate description of the FD is necessary at the inlet plane. Several distribution functions have been proposed like logarithm and probability density function, Russell-Lamla distribution, Nikuyama-Tanasuo distribution, NT distribution. So, these are the distributions which are actually available. This is a droplet size distribution, how that varies, and this is a one case you can see how things actually for different these things they changes. Now, if you look at the transport for the DDF, this is derived for like this, where there is a collision term, this term Rj is the change of size r for a particle composition, Fj is the particle composition at j, this is the increase of Fj due to spatial element. So, the simplified form one can write in this. Now, if you look at this complete picture, so either there could be locally homogeneous flow, so the phases are in mechanical and thermal equilibrium, or it is a separated flow. Then there could be continuous formulation model, there could be discrete droplet model or continuous droplet model. Now, continuous formulation model, both phases are continuous, difficult to define droplet heat up, turbulent stresses and dispersion. Alternatively, in continuous droplet model, it is Eulerian PDF of spray PDF, computationally prohibitive. Now, the approach which proposed by Crow in 1977, the discrete droplet, where the stochastic flow model or deterministic separate flow model. So, this is finite slip interface transfer rate, this also has finite slip interface transfer rate, effect of turbulence on dispersion, these are considered. So, that gives you an idea what goes on. Now, classical SSF approach is most popular among different dilute spray model originally developed in context of RANS. Now, effect of both finite slip between the phases and interface transfer rates are considered. Effect of velocity fluctuation are also considered on droplet dispersion, heat and mass transfer rate, structure of the gas. So, these are some of the issues associated with the stochastic separated flow model, which one can note it down. Now, you can have this Lagrangian Eulerian modeling, where your fluid phase or the gas phase is solved in the Eulerian framework, and the liquid part is solved in the Lagrangian framework, where we track the particles. And so, obviously, it becomes important that it is just like your transported PDF calculation, where you have so many particles to be tracked within the computational cell. Now, in a continuous phase model, there could be one can do fully resolved DNS, which is basically the droplet particle latent flow where the exact initial equations are solved, or point particle DNS, which physically droplets or stochastic particle, or point particle LES. Now the LE approach discussed so far couple the Lagrangian tracking of the computational particle to a carrier gas flow based on the RANS equation. Now these are the approaches one can actually adopt and take into consideration. Now we can start looking at the background on the discrete phase model or DPM model. The trajectory of particles or droplets are computed in Lagrangian frame. So this is the trajectory, and then we have capabilities of coupling this particle to gas phase in the validating phase. So we can update the continuous phase source term and move to the continuous phase calculation. That there are certain specific requirements one has to keep in mind if you are using the discrete phase model. It is recommended that you keep a volume fraction is less than 10%. So the reason for that is because the discrete phase model does not take into account any particle interaction. So particle do not know about the another, and if you are at a volume fraction much higher than 10%, then the influence of particle interaction may become significant, which can alter the. So this is what you can calculate the trajectories in the heat and mass transfer. Discrete volume fraction should be preferably less than 5%. So mass loading can be large, no particle interaction or breakup. So turbulent dispersion can be handled by stochastic tracking and multiple cloud model. So the model particle separation, spray drying and all these things. Now the coupling process, there could be one-way coupling where fluid phase influence the particle phase via drag and turbulence, particle phase has no influence, or two-way coupling where both fluid phase is influencing the liquid phase and the liquid phase is also influencing the fluid phase, and four-way coupling. So this is in dense spray, particle gas phase, and all these interactions are important. So there are multiple ways one can couple this, and this picture will give you an idea where you have a negligible effect of turbulence, which is one-way coupling, and this is where particle enhanced turbulence, particle decay turbulence. So this is two-way coupling, fluid particle interaction. So this zone goes to dilute spray or dilute suspension, and this is where the four-way coupling is important in the dense region. So there are Stokes number and the time scale of all this can be correlated. Now atomization being so important, one can look at this snapshot when it comes out of a nozzle exit, how it goes through. So there is initial seat and then slowly becomes, and this is how the droplet diameter distribution in the 3D. So this most of the droplets have been generated by shedding of mushroom shape. A generation of the breakup of ligaments occur in many different phases through the wavelength of the jet. These ligaments further break into polydispersed fine droplets. So basically there is a liquid comes in, there is a ligament and all this. So this picture shows you more details. This is how it is comes in, then goes through like this, and finally you get this fine set of sprays. So there is a primary, there is a breakup length, droplet formation, secondary breakup, drop collisions, everything is included. So this disintegration of liquid jet or the seed by kinetic energy of the liquid, so which is exposure to the high velocity air or gas or by mechanical energy. So this gives you an idea when the liquid is actually injected, what kind of process it goes through and what is the. Now the primary atomization, which actually involves the formation of the ligament near the surface of the liquid jet and undergoes further breakup. These droplets undergo secondary breakup and then fuel air mixture initiate the atomization, controls the exit of the liquid core. So now this is how there is a seat region, then lumped region, then the filament region, and then the atomization which takes place. Now there are jet breakup models. In the primary breakup there could be cavitation and turbulence model, wave breakup models or Kelvin-Helmholtz model, Bob injection or seat atomization model, and there is another one which is quite popular, this is the LISA. Secondary occurs downstream in the spray. So this is the spray boundary, this is somewhere the secondary breakup, this is the primary breakup zone. So the Ridge-Dewar model, Tab model, Kelvin-Helmholtz, Rayleigh-Taylor. So these are the. Now the droplet formation and Secondary breakup regimes are function of the wave number and Asnar's number. So, this is the wave number, which is a proportional to aerodynamic force to the surface tensor probe, and OH is liquid viscous force to inertia and surface tensor probe. So, the droplet breakup regimes, that could be a parachute type where the droplet flattens. So, it depends on the wave number range of the flow eventually from say shroud. There could be stripping type where the droplet flattens perpendicular to flow and the gas flow tears the shroud, and explosion type. So, this picture will give you an idea. This is a back breaker or the parachute type where the Weber number is like this, the air comes in and this kind of breakup takes place. Now, the stripping breakup, this is a Weber number range of 20 to 20,000 where this kind of breakups or the catastrophic breaker or which is a explosion type. So, depending on the Weber number, so this is a very important non-dimensional number which plays an important role in the atomization model. Now, the TAB model, this is an proposed by O'Rourke on 1987. This is spring mass system balance between surface tension, droplet drag and the viscous forces. So, it is best suited for low Weber number space. Extremely high Weber number space result in scattering of droplets. Now, the wave model, here the droplet breakup is due to aerodynamic interaction between the liquid and the gas leading to Kelvin-Helmholtz instability, which growing to the surface of the cylinder called jet. Here it considers the breakup of the injected liquid to be induced by the relative velocity between the gas and the liquid phases, and the model assumes that the time of breakup and the resulting droplet size are related to the cage instability growth. So, here the collision and the coalescence, this is based on either there could be coalescence or there could be grazing collision. So, the coalescence occur if the impact parameter is lower than the critical value. So, the number of coalescence for each collector is then found and used. Now, the diameter, velocity, temperature of the collector drop after coalescence is calculated from mass, momentum and energy conservation. Now, if the original number of the droplet in the droplet parcel is lower or equal to n, the droplet parcel is removed from the calculation. Now, when you come to the grazing collision, if the impact parameter is bigger than the critical value. So, the grazing collisions usually occur between droplets of approximately equal sizes. When grazing collision occurs, only momentum is exchanged between the droplets, and the droplet diameters and temperature, this remains unchanged. So, this is what the actually the situation. Now, there could be particle conditions at walls, so it could escape, or when it hits the wall it could reflect, or this could be trapped. So, the particle, the restitution coefficient E is specified and that can be estimated. Now, the trajectory is calculated by integrating the particle force balance. So, this is the drag force, gravity force, additional force due to pressure gradient or thermophoric or rotating frame of, and then the dilute spray, the CD would be like this, dense spray, the CD. So, these are the correlations which are available in literature, that which is very common. Now, the collision of heating and evaporation models. So, you can have Spalding's evaporation models like this, the constant droplet temperature model, D2 law, infinite conducting model or finite conducting model. These are also well established, or effective conducting model where the ECM is an extension of FCM, amount of the internal liquid circulation. There could be vortex models. The internal liquid circulation is modeled using a predefined velocity field, Hill's vortex, or Navier-Stokes solution or Stefan flow. So, these are some of the ways one can classify the heating or evaporation models, and these are now the widely used approaches to model the Stefan flow effect. So, these are the equations, and this is the source of the informations where you can see who has proposed based on what kind of these things. Now, the important thing is the interaction between droplet and turbulence. Now, the stochastic separated flow model or SSF model, the effect of turbulence only droplet motion is considered by a stochastic approach by due to decoupage. and then the gas phase local and instantaneous velocity is obtained by adding the fluctuation component. So, then you can see how this turbulent time scale is actually. So, it is assumed by a randomly sampling Gaussian distribution and then calculated. Now, these are the different turbulent combustion model where we have already seen eddy breakup, presumed shape, transport PDM model. Now, these are the two advanced models which are conditional moment closure, where the conditional scalars are solved, high computational effort, evaluation of reference variable and high computational effort. Now, the challenges, you have conventional definition of mixture fraction is not conserved for sprays. So, we can directly extend mixture fraction based conserved scalar approach to CMC and all this. Now, two phase source term in the transport equation for mixture fraction variance. So, scalar dissipation rate is another thing, and flame envelope and all these things. So, flame envelope one can look at these things. Now, we can quickly go through the RANs and LES of spray combustion, what is available or what have been people doing it. This is the particle approach, their locations and their velocity, how it is estimated. So, this is UP, then you can get the drag coefficient like this, and this is the droplet Reynolds number. Now, we have mass balance, energy balance, Nusselt number calculation, Sherwood numbers, Paulding numbers and Clausius-Clapeyron equation for vapor liquid equilibrium. So, these are the important equations, and then there could be single or group injection, how the particles are injected, there could be cone injection or there could be surface injection. So, depending on that, and in practical spray system we encounter complex flow behavior. So, measurement close to the nozzle is not possible. So, we need well defined boundary condition for both phases at the inlet plane of the model validation. So, this is an important point because these measurements at these planes are not that easy. These are the set of equations. So, you have continuity equation with a source term, momentum equations with spray source term, evaporation term, kinetic energy, where there will be source term, dissipation source term, mixture fraction there is a source term because of the second phase, and variance equation also, and this is your scalar. So, the equation system we have discussed in details, but what I am trying to mark here is that these are the changes that one will encounter due to the second phase. Now, two phase, this is Crowe et al. Proposed, the mass Sm would be number of particles and calculated momentum energy source. So, there is a fairly good amount of literature which is, or rather fairly established literature which is available to close those terms. How these things work? So, we have initialized the flow, we solve in the gas phase, then this information of the mean field passed to the second phase, where we use the evaporation model. Using the mean field, we evaporation model that comes back, we use our injection of the spray, then estimate the fluctuating velocity and finally get back u prime, and then finally the gas liquid coupling term, the source term goes back here and again it solves. If it is convergence stop, otherwise goes back. So, that means one hand the mean flow will send the information back here and then it goes back like this. So, particle tracking, cells should be crossed in minimum 2 cells. So, this is typically the way we have handled in the transported PDF approach, the similar way one can handle this. Now, similarly, LES case, you have a source term here in the momentum one source term, there is a source term in the mixture fraction variance, then the variance equations. Now, another is the group combustion. So, in a practical combustion, it is quite difficult to follow each particles which are present. So, there is a ways one can actually characterization is done in terms of average quantities related to the drops, average numbers and all this. So, this is developed by Chiu, that group combustion number which is defined as a ratio of the heat exchange between two phases and the rate of heat vaporization. So, depending on this one can have external sheath combustion where this group combustion number G greater than 100. So, this consists of a inner non-vaporizing cloud surrounding by the vaporizing droplet. Now, there could be external group combustion where it between G1 to 100 and inner vaporizing cloud with stand-up flame, spray cone temperature higher than this, or internal group combustion or the single. So, you can find out in this details that what are these. Now these are the some of the spray burner which are available in literature. I mean, people have done calculations on these burners. So some of the example, this is an alias of gas phase. I will show you some, I mean, how it is handled. Some, so this is an your models where you had, this is based on mixture fraction based. So this is how alias, you have filtered equation, you pass that equation in the Lagrangian flow field, you solve it, you have a local flame structure which is tabulated and sent back and they are coupled. And this is how you couple that in the continuity, mixture fraction, momentum, the second phase or the spray source term. Okay. And these are the some of the results which is from this literature, where you can see use the LES progress variable kind of approach to compute the. Then there is another one in the conditional moment closure, which is initially proposed by Klemenko and Pope, but later on it was used by different groups, and where actually the gaseous phase we have seen that conditional moment closure approach, this is now extended for multi-phase, and there will be some terms and you can look at these references for details and you can see the predictions how that comes through. These are the some of the images from that. And of late there is one more advancement which has been taken place is the, or this one could do the transported PDF approach. You can go through this literature where they have used the LES. So I will show you some of the images that how you can, this is the non-reactive case, this is the reactive case, and this is the fuel. This is, you can see those images from there. Now there is another approach which of late got more attention is the multiple mapping closure. So this has been, this is using I mean the advantage or combines the effect of PDF approach, I mean the transported PDF approach and the CMC. So combining this, so one can have stochastic MMC or deterministic MMC, and one can look at this recent article where you can see the details of these things, and these are the equation system. So essentially you solve in the particle phase and the gas phase mixed with the gas phase, and these are some of the calculations what you can see there using this advanced MMC structure. So that pretty much gives you an idea what you can do and what are the models you have in the handling the multi-phase system. So you have all the gas phase models which we have discussed that are required, and top of that when you go to multi-phase system you have all these source terms which are arising due to the droplet, and the droplet combustion itself is complicated. Top of that the droplet is formed through the atomization process and all this. So that will give you a fair amount of idea how the multi-phase systems are handled, and I hope this will give you a good fair amount of idea about this turbulent combustion modeling and their recent advances. I hope you have enjoyed the course and we will take it forward. Thank you very much.